Good afternoon, ladies and gentlemen. So we're going to try this again. I certainly didn't just make a video that didn't work at all. No, not at all. So we need to be able to look at reactions and figure out who is gaining and who is losing electrons. So we have to be able to look at some of these old equations like this, and when we look at them, figure out how the oxidation states are changing. It can't hurt to write on the question as long as we are careful. This is magnesium and the solid. It is not bound to anyone. It is magnesium with no charge. On the other side, we have magnesium that is a positive 2. That means that magnesium is losing electrons and therefore is oxidized. The hydrogen is a +1. On the other side, hydrogen is in its normal state. It is a 0. So it is gaining electrons or being reduced. So that one's pretty easy because you could kind of tell who's changing to what. Oxidation states are either written in there or need to be determined very carefully. The iron in B is pretty easy to figure out. Does it fit on here? Doesn't quite all fit on here. The iron is a +2, and then the iron is a +3. So it is definitely losing electrons. Alright, what about the hydrogen? Okay, the hydrogen is a +1 on the reactant side. On the other side, what is hydrogen in this water? So here's water. Oxygen is a -2 charge. There's 1 oxygen, there's 2 hydrogens. Hydrogen is a +1. Therefore, if hydrogen was a +1 and it is still a +1, it has not changed its oxidation state. So neither Leo nor Ger. This permanganate ion has a manganese in it. We have the manganese's charge on the product side as a +2. We're going to have to delve into this permanganate, figure out what is the oxidation state of just the manganese. We used to do this all the time back in our redox chapter. We have 4 oxygens. Each oxygen is a -2. 4 times -2 means these combine together for a -8 charge. All of the pieces add together are -1. So the manganese has to be a +7. The manganese is going from +7 to +2. So that is 5 electrons. It is gaining 5 electrons. But the iron's going from +2 to +3. +2 to +3, that's only 1 electron. But there are 5 irons. So the 5 electrons lost by the irons are equal to the 5 electrons gained by the manganese. So we've figured out which elements are gaining and which elements are losing electrons. Remember that losing electrons, oxidation occurs at the anode. Cathode is where we Ger. A Leo, cat Gers. The iron is losing electrons. The cathode is gaining electrons. That just means that in the solution, I'm going to draw 2 beakers. Wow, look at those beakers. Those are great beakers. Then we've got our U-tube, some sort of salt bridge connecting the 2 beakers. And then there must be that piece of metal and a different piece of metal. What connects the 2 pieces of metal together? A wire. You know what? I'm going to change colors. A wire. There we go. And when they're connected, the circuit is completed as long as everything is dissolved in some sort of solution, and then electrons can flow through the metals, through the wire, to the other metal, to this solution, ions can flow through the salt bridge and keep it going. Or it could go the other way. It just depends on which side the anode is and which side the cathode is. So if the iron is on this side, if the iron plus 2, iron plus 3 solution is on this side, this would be the anode. Actually, that's the metal here would be the anode, and the electrons would be pulled up. The electrons would go through the wire. This is where the electrons would be lost from this side. We come down through this metal and then be gained here in the other beaker. This would be our manganese solution, where the manganese is going from +2 to +7. Scratch that, reverse it, +7 to +2. And then the ions would be flowing through the salt bridge to keep the whole thing neutral. And let's pause. So the cathode is where the electrons are coming into the solution. The anode is where the electrons are leaving the solution to travel through the wire. And then the salt bridge allows ions to flow through it. Make sure you practice ripping apart polyatomic ions. This phosphorus, these 4 oxygens add up to being -3. Oxygen is a -2. That's -8. So the phosphorus is probably a +5 oxidation state. Got to get good at that again. What else do we have in here? We have a blank page because we're about to talk about voltage, and a lot of times people struggle with the concept of voltage versus amperage. So let's talk about voltage versus amps for a second. And you know, I always like to present concepts with analogies. So here, this brown stuff represents the ground, and then here we have a baseball. We have a baseball. It is at some height, and because it's at this height, it has a potential energy because it could drop down. Another baseball is at a different height. This height is about double, so its potential energy would be twice the potential energy of the other one, because potential energy is equal to mass times gravity times height, or something like that. And then it could be converted into actual energy as it falls down. Well, in both of these scenarios, what is pulling on the ball would be the mass of the Earth exerting a gravitational force. Well, in our world, we will not have the Earth pulling on electrons. We will have one metal, let's say copper, pulling on the electrons in another metal, and they're both pulling, but one of them pulls more. Whichever one pulls more is going to actually pull the electrons to it, and the electrons will shift from one element to the other element based off of which element is stronger. But I think we can agree that a copper atom should have a consistent pull, because a copper atom is always a copper atom is always a copper atom. And a zinc atom is always going to pull the same way. And so if we measure their pull value once, we will know their pull no matter what. This is just the difference in strengths, though. This difference in strength is what we call voltage. It is the potential energy when comparing two elements against each other. This does not measure how many, it measures the distance. It's the distance between the two. If you want to measure how many electrons, you switch over to the other side. This is the amount of electrons per second versus the amount of energy. Get the units right? Looking for them somewhere here. Yep. The amount of energy is joules per coulomb which is a volt, versus coulombs per second, which is amps. We will get into amps a great deal, but just to keep the analogy running, baseball this height, same height, way more baseballs. Person standing here, person standing here, person standing here. Whole bunch of baseballs. Looks like the people keep growing in size. Let's try to get back to the original size. The few people on the right obviously going to get hit by a lot of baseballs when they fall, and it's going to do a lot of damage. But the voltage between these two sets is identical, and obviously amperage is a much bigger deal. All of these falling would even be more than this one falling. Amperage is a much bigger deal than voltage. Now, if you have amperage and voltage increasing, that's also a big deal. It's a lot more energy released. Typically, people say it's not the volts, it's the amps you have to worry about, because the amps represent the amount of charge that's moving in a second, not how much energy that charge has. So the amps are more how many disruptions you can have in a second, how many charges you can have in a second. We're going to focus on voltage for the next couple minutes. Remember, voltage is the difference between atoms and their pole. There are many different types of reduction potential charts out there. You do not have this chart in your notes. It's actually from your textbook. So let me just kind of scroll down, and you can see that this chart is a pretty long list of different poles of elements, but you have to have some sort of basis around which it's all based. So let's say we had a big tug-of-war match here in class. I have to set up a basis for the pull. So maybe I have everyone pull against Arthur in the class. So you have Arthur one half of the rope, somebody else the other half of the rope. We pull, we measure what happens, and then we could say you're stronger than Arthur, you're weaker than Arthur, you're stronger than Arthur, you're weaker than Arthur. And then based off of how long it takes, we could kind of line up everyone in the class around the strength of Arthur. I'm 2 times weaker than Arthur. I'm, a little bit stronger than Arthur. Well, no one's drastically stronger than Arthur, but you could kind of set everyone up based off around Arthur. With chemistry, they have based everything around hydrogen, because, shocker, hydrogen is pretty available. So they've defined hydrogen as 0, which would be like having Arthur have a tug-of-war match against his identical twin, who we'll call Arthur, and no one would win because they'd have equal strengths. All of these other elements are stronger or weaker than Arthur. The positive ones are stronger. I said stronger or weaker than Arthur. Stronger or weaker than hydrogen ions. And the ones that are positive are better at taking electrons, and the ones that are negative are not as good at taking electrons relative to hydrogen. As you move up, you get stronger and stronger, meaning better at gaining electrons. The ones at the top are very good at reduction. Fluorine is really good at taking 2 electrons and becoming fluorine -1. Chlorine, that fits with some of the things we know already in our lives. When you get towards the bottom side, you have a bunch of very weak metals. Look at these alkali metals down here. They are not very good at taking electrons. They would be better at losing electrons. So if you flip this chart around, this chart flipped becomes an oxidation chart, and then the best oxidizer, the element that's best at giving away electrons, would be lithium, producing lithium ions +1. That would probably be the best oxidizer on the chart, because it's really bad at taking electrons, ergo very good at giving electrons. Lithium's a very giving element. And so what we will do here is we will pick 2 elements and we'll kind of compare their strengths against each other. Let's just go back to the classic zinc And we'll do silver. Zinc versus silver. So which one is stronger, zinc or silver? Silver's higher on the list, so it's a better reducer. It's very good at it's better at taking the electrons away. Zinc is better at giving the electrons away. So if we write this zinc reaction in reverse, its voltage would go from a negative to a positive 0.76 volts. And then you have one reaction giving off electrons, and the other reaction taking electrons, and the 0.8 volts of the silver and the positive 0.76, now that I flipped it around, of the zinc has a total voltage of 1.56 volts. So it's kind of like saying the electrons would fall 0.8 to get down to here, and then an additional 0.76 to get down to here. So you can consider hydrogen like the ground level. It's falling and falling a little bit further. Again, we flip this negative to a positive because the sign is flipped when the reaction is flipped. Let's look at some examples of that. Right here you have magnesium becoming magnesium plus 2. That matches with this equation. Magnesium's becoming magnesium plus 2. So we already have the voltage for that one. The other one is being reversed, but if you flip hydrogen around, you go from positive 0.00 to negative 0.00, and negative 0.00 is not really a thing. But so we can add the magnesium down here. We can add the magnesium value and the hydrogen value together. So the combined voltage should be 2.37 when you add these two values together. The copper and silver one. Let's see. Copper plus 2 is a reactant. Here it is a product. So I need to flip this around. So this becomes positive 0.80 volts. Silver is on the correct side. Oh, wait a minute. That's one silver. I need two silvers, two. And this becomes, nothing changes here. Mr. Murphy, if you double the silver and the number of electrons, shouldn't the cell potential change? Shouldn't the voltage change? If I double the number of balls at this height, is the potential energy drop greater? No. Each one is still falling with the same amount. We have just changed not the potential drop, but the amps, how many are dropping. Amps and voltage are different. So I know we doubled the amount of silver in the second part, but that just means that the voltage is still the same, just reversed. So the sign, the sign of copper is reversed. The sign of the copper is reversed. The voltage of the silver is still the same. Combine those two values together. What is 0.8 and negative 0.34? It is 0.46 volts, 0.46 volts. So the number of electrons does not impact the voltage, but rather the amperage. We will deal with amperage at the end of these notes, not right now. Here's another example of that. We're flipping. We always want to make sure that the voltage is positive. So when you see two reactions, you figure out which one is better at reduction, better at gaining electrons. In example A, the oxygen and the hydrogen becoming water is a positive 1.23 volts, which is much greater than negative. I have to flip the first reaction. You may not have electrons on the reactant side for both of them. One reaction has to be losing for the other to be gaining. It's just basic economics. One is gaining, the other is losing. So I had to flip A around, and when I flipped A around, I got a positive 0.23, and positive 1.23. So the combined voltage is not a check mark, that's a really wide V. The combined voltage of these two things is 1.46. Same thing in B, I had to flip around the weaker of the two and then added them together. No big whoop. This, of course, is only true at standard conditions. Standard conditions, 25 degrees Celsius, 1 atmosphere, 1 molar, that sort of stuff. If the voltage was not, if the pressure and temperature and molarity were off, they might have an impact on our calculated voltage. We will be dealing with that later in the notes. Line notation's not terribly exciting. It's just a way of representing what is going on. If you look in your textbook, you'll see that they line the anode is always up on the left, the cathode's always on the right. Losing electrons, gaining electrons, whoever's on the left. So there's a line separating the two pieces. There's a line separating what's going on in the cathode. And there's a double line that separates the anode side from the cathode side. It's supposed to represent that disk, the salt bridge. So we always have what is losing electrons, what is gaining electrons, anode, cathode. Yeah. Here we just kind of like a zoomed in version of what's going on. The zinc is losing electrons, the zinc losing electrons, and you have zinc atoms coming off into the solution. So you'd be gaining zinc atoms in the solution. On the other side, the coppers are going from copper +2 to solid copper. So those +2 coppers are actually attaching themselves to the copper, and you would slowly have more and more and more and more coppers building up on this piece of metal, and the amount of copper ions in solution, would drop as this battery was left to run, and the electrons flowed through that circuit. And here's just some more examples of that. Make sure you can look at an equation and pick out the anode and cathode. Why don't we pause the video for a second and write down which ones are anodes, which ones are cathodes, and how things are moving. All right, there you go. And then you have, the anode is always going from one, it's always losing electrons, cathode's always gaining. You could even look at that from the beaker perspective. The anode is the one where you have metal ions going into solution, or in solution there's electrons lost here, electrons are gained in the cathode every single time. That of course means that the circuit's complete. If this wire is broken, none of this stuff is occurring. The electrons have to flow through the wire. The wire actually has to be connected. So what have we learned? We've learned how to calculate cell potentials given voltages. We've learned how to describe the electron flow through the wire from the anode to the cathode. You have to figure out who's who. You have to be able to label them. Yeah, I'm going to give you pictures. You have to be able to label them. We talked about line notation. So here's one last example on the topic. We have copper versus dichromate to figure out which one's a better one to flip. Obviously we're flipping the copper because I wrote flip right there. But if you look at the two voltages, you wouldn't want to flip the larger value here, because then when you add them together you'd end up with a negative voltage. We're flipping the first one, so we go from positive 0.34 to negative 0.34, and then we add them together. The combined voltage of 1.33 and negative 0.39 is a combined voltage of 0.99 volts, almost a whole volt. And these two could be kept in two separate beakers. You wouldn't have to actually mix them together and have the electrons flow through the wire. They would leave the copper side and go into the chromium side, because the copper is the anode and the chromium parts are the cathode. In this particular case, the chromium is dissolved the entire time. So as these electrons are coming through the wire, they need something to deliver the electrons into the solution, because both the dichromate and the chromium +3 are ions that be in the solution. So this piece of metal would have to be some unreactive element. These are typically platinum and gold electrodes that will deliver electrons without reacting. That's why platinum and gold are such valuable metals, because they can stay being just their plain old boring gold or platinum selves. They're good at moving electrons around without actually reacting with other elements. So we don't have if we had gold oxide forming all the time, people wouldn't wear gold. So that's what I'm saying. Alright, before we start the last piece, I'm going to stop this video and start number 3 in 1, 2,